This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right. Maybe I will try, because by the time I'll finish saying my things, then I'll give Wenbin the floor or the screen to present the speaker. So hi everyone. So I guess most of you know me from the association. If you don't, then I'm Itai Einav, and I'm actually the president at the moment of the associations. We have what that means is that we have a monthly meeting with the committee. Wenbin is, for example, is the secretary and of the committee, and we have here Francois, who is the treasurer. There's some other members that will join probably soon, some cannot. The purpose of the association is to elevate, first of all, research of granular materials in Australia, in the academic circle predominantly, but also industrially. More and more. In addition, one of the points here, for example, was the introduction of a code that those that don't, many students here would not know, code that is important for the Australian Research Council. So we got our own code. Other more important maybe aim is to bring students together to educate students, and thus we have annual meeting called Grain Days, 2 days events. It will be the 5th one, is upcoming in November. You would have received probably information about that. It's really mainly for students, but also for any staff that wants to present their work in another day. Point is to create regular annual events where the first day is a school, and this year, for example, the school will be on computational methods. We have also an experimental and theoretical method, so we kind of have every 3 years a circle. So about 4 years ago we had the numerical or computational theme, and now it's recur. So this year we are going to have it again with 3 talks. And on the second day we have of Grain Days, we have basically presentations. So here staff can present, but mainly students. So students, we hope, will present either in a bullet presentation, 3 minutes, or in a posters. So please do submit your interest. We are here to support students. And we have lab visit typically. This is how it goes. So this is one thing that happens quite regularly now. Now, the committee has decided to bring a new idea. And today we will initiate that. So today is the inauguration of that event. So we are going to have a webinar series. Yes, we are all, in a way, very familiar with webinar series. We are going to have our own webinar series, but it's not erroneous. We are not going to bombard you with many meetings. The idea is to come together, see each other, learning new ideas, and bring new members and new groups. For example, Anthony's group, we are hoping all of that group will join us, because we want to welcome as many people as possible. So, and we want to learn new ideas. There's people from chemical engineering, from physics, from civil engineering in my case, for example, and all sorts of engineering and walks of life, mathematics, and so on. So we want as many people from as diverse group as possible, and if you have recommendations, please do, and we would welcome them for the event. So now I will stop here, and I will ask Wenbin to introduce our inaugural speaker for the webinar. Thank you so much.
Thank you, Itai, for the introduction. So as Itai said, so this webinar is for education purpose, and we want to include so people from different departments. So like the first speaker here today, Anthony Stickland, is from the chemical engineering in the University of Melbourne, and he's also lectures a lot like the powder technology, particle technology, sustainable mineral and recycling, and fluid mechanics in the University of Melbourne. Yeah, Associate Professor Anthony Stickland, so is also a chief investigator in the ARC Center of Excellence for enabling eco-efficient mineral beneficiation, and leads researchers like in particulate suspension rheology and solid liquid separation. And his research covers material characterization, models of processes, and suspension dewatering and handling. And his group works closely with industries such as water treatment and minerals processing. And today, Professor Anthony will give us a course about solid liquid separation of compressible suspension, and which is very useful for mineral processing, water treatment, and food processing. And without further ado, I will give the floor to Professor Anthony Stickland. And yeah, here you go.
Thank you very much for the introduction. So you're seeing my screen now. If you're looking for, as an aside, if you're looking for members, there's lots of people up at Newcastle University in chemical engineering who do a lot of work on particles as well. So if you go and have a look for Ken Williams and Kevin, I'm having a mental blank. Kevin Galvin.
Yes, but we are in touch with both of them. Thanks. Yeah.
Okay, so Wenbin invited me to come and give this webinar, and as he mentioned, I teach a subject called particle technology in the chemical engineering degree. So there was a lot of things that I could talk about, but in the end, Wenbin and I discussed it, and we decided that this talking about my area of research in particular would be of interest. So just briefly, I'll introduce my research group. We're called the Sludge Group. It gives a bit of a flavour for what the research is all about, really. There's a couple of emeritus professors who are involved with the group, Peter Scales and Robin Butterham. A couple of postdocs, Shane and Nalenka, and then Raul Cavalita is the lab manager, and then a series of PhD students in a range of different projects that are interested in mainly minerals processing at the moment, because that's where most of the funding is coming from, but also in water and wastewater treatment. Some more on the experimental side, some on more theoretical side. In particular, today I'd like to talk about small particles. And so here's a scanning electron microscope image of some fused silica, and you can see the scale bar that the primary particles that make up this are submicron, and the aggregates of order microns in size, made up of thousands of primary particles. In general, if we talk about particles in a fluid, we can divide it up into what happens in air, and we can have various powders such as dust, smoke, grit, grains and sands and so forth, or we can put them into a liquid, and we have a lot of great S words like sludges, slurries, sediments, slimes, silts, soils, etc., etc. Pretend I'm a snake. And a few non-S words like muds, clays, precipitates, residuals, etc. And so, depending on whether we've got it in air or in liquid, completely predictates or dictates what the behaviour is going to be like, because the two have very different viscosities. And so, in air, there are virtually no viscous effects. It's the inertia of the particles and so forth. In the liquid, all of the rate is determined by the drag around the particle. I'm also particularly interested in small particles. So as you get below 50 microns or so, as you get smaller and smaller, of course, your relative surface area increases, and therefore systems which will have a net attractive force between the particles lead to the things like the image in the background here, where you've got lots of cohesive particles that are all sticking together and forming a larger structure. So that's my research is on small particles in liquids, and today's presentation is going to be predominantly this side on the right. Where's my laser pointer? So over this area here. So in general, we're interested in a range of effects when we're looking at powders or suspensions. In particular, the main things that are going to affect the behaviour are how many particles there are per unit volume, so the concentration, the size and the shape and the distribution of those of the particles within there. What are the forces acting on those particles? Generally, gravity, usually, if it's sedimentation, or we might be applying a mechanical force. And lastly, what are the interactions between those particles? Are they repelling each other because they've both got the similar charges, or are they attracted to each other because of van der Waals attractions, or I might be adding a physical polymer that might be bridging between particles to make them sticky. And the things that are then going to be affected by the size and the shape and all of those are how is it going to behave when we put it into some sort of application? So how is it going to flow, or the rheology of the material? What's it going to pack to in terms of its density or porosity? If I make aggregates out of it, what are the strength of those aggregates and the cohesion between the particles, and then leading to the bulk cohesiveness of the powder? How do powders and suspensions mix? How do they segregate? And lastly, what's the drag between the fluid and the solid? And in that case, what's the rate at which the particles will move? So today I wanted to cover these topics. I wanted to look at a range of different devices that are involved in solid liquid separation, or the shorter word, dewatering. What are the basics, and revisit some of the textbook equations that might be used, and then explain why I think they're wrong, and then come to the area of compressional rheology, which is my research area. I'll look at the basics of the equations that you would look at using for gravitational processes and filtration processes. I'll then look briefly at a couple of related topics of cake washing and desaturation. And then lastly, I've got a slide looking at modelling and optimisation. Hopefully, I won't talk for the full time, but I do have a habit of waffling on sometimes. When we're looking at industry and the way in which the solid liquid separation typically occurs, as in particular, say, the minerals industry, what usually happens is that you get some primary particles, which are these green blobs here. You might add a flocculant to them, or they might be want to coagulate the particles with a chemical or something like that, and you create what I'm representing as primary particles that are held together with some sort of bonds as the red bits. They will form a flock or an aggregate that is usually then settled under gravity. Gravity is usually the first separation step because it's free. You don't have to pay for the driving force. It's not particularly strong, so it doesn't happen that fast or with a small footprint, etc. But gravitational thickening is the most common initial step in things like water treatment, wastewater treatment, mineral processing, etc. once we start settling those materials, they form a sediment or a bed of material. That bed now has a completely interconnected series of particles that are holding it all together, and that's able to transmit a stress. If I apply a force on the network but allow the liquid to be able to come out somehow, like squishing a sediment or putting it in a filter or something, if I apply enough stress to overcome the interparticle strength of that network, then it will fail and the fluid will come out, and the fluid will come out at some rate given by the viscosity and the porosity of the bed. There's a range of different ways I can apply a force onto a network to make it dewater. I can use gravity. Like I said, that's the weakest and the cheapest. I can increase the gravitational the acceleration value and put it in a centrifuge. So enhanced sedimentation, you could call it. I can put a membrane or a filter cloth or something in the way of the particles and stop them from coming through and let the liquid come through. And I've got different options there. I could use a vacuum, essentially sucking the suspension onto the filter cloth, or I can use a pump to push it with a positive pressure against the filter cloth, i.e. a mechanical, a filter press sort of thing. I can also evaporate off the water using drying, or either solar drying or thermal drying. There's a last one here I've got with the brackets around it. I can use a shear stress, or a lot of dewatering processes include shearing stresses. Now, shearing by itself won't cause a dewatering. You need to have something to cause the particles to come closer together, whether it's just gravity or you're applying a force to it. But shearing will help to break down that network. And so as I'm trying to squish on something, there's a chain of particles, a force chain that's supporting that network, and by pushing it from the side, that helps to break that chain of particles and therefore help in the dewatering process. So I've got shear stress in brackets there, and I'll highlight a few devices that include that shearing. So a couple of slides on just some processes that do include these sorts of mechanisms. The simplest is gravity-driven thickeners, where material is fed in at the top through a feed well. It gets mixed with a polymer flocculant, usually a long-chain polymer that will bridge between particles, but there's a range of different mechanisms that you can flocculate things with. And essentially the gravitation, the density difference between the particles or the flocks and the surrounding liquid causes the flocks to settle. They'll settle down into a bed of material, and then the compressive forces, because of the weight of the particles, will cause further dewatering in that bed. Thickeners, or conventional thickeners, can be up, well over 100-meter diameter sorts of things. Escondida, the world's largest copper mine, has 11 thickeners, and they're 125 meters across diameter each. So you can imagine they can be very large objects. They're typically the conventional thickeners, where they're fairly low velocities going through there. There's not a lot of flocculation going on, but they're very wide diameter. There's not a lot. They're very shallow. Not a lot of bed there. And so the concentration that comes out is just at what's called the gel point of the material. As more and more recent or advances in thickening technology have brought the diameter down and increased the height. And so now you have high compression and paste thickeners, which have a large bed of material that's providing the compressive force to densify the material at the bottom. I could talk for the entire hour about thickening if you wanted to, but I'll keep moving. Different types of filters that you see. There's things like vacuum drum filters, which is a large cylinder with a filter cloth around it. The inside of the vacuum is the inside of the drum is under vacuum, and as it passes through the slurry bath, it builds up a cake, then comes out of the slurry bath. The cake can compress a bit, then might desaturate, or you can even use a washing step on that before the cake then gets scraped off. This is a picture here of some of these drum filters. An alternative version is a disc filter, which a whole series of discs that are usually ceramic discs, or they put a filter cloth over the top. And you can see the disc filter here. Vacuums are of course limited to atmospheric pressure. And so if I've got a very, very fine particulate material, then the vacuum is not going to be sufficient to, for example, desaturate the material. If I get down to about 10 microns, depending on the surface tension and various other things, I'm going to have a capillary pressure in the pores that is of order 100 kilopascals. So I'm never going to be able to desaturate the material. I would need a hyperbaric version of these, which do exist. So they put the entire drum or the disc stack into a hyperbaric chamber so they can get larger pressures. Another alternative source for filtration is to use belts. And essentially you feed material onto some sort of feed section. It undergoes gravity drainage on the feed area. So this is a picture of the gravity drainage area for some sewage sludge. Before it then gets squeezed between two belts, and the belts are under tension as they go around these rollers here, and the tension is causing the dewatering to occur. Belt presses have a little bit of this shear effect because the belts are actually, have the thickness of the cake. One has a larger radius than the other, and so as they're going around each roller, they're actually moving relative to each other, or there's a force acting on that, which provides an enhancement. If we did the calculations and showed that if you were just relying purely on compressional dewatering, there was never enough time at as it went around those rollers to actually achieve what you see in industry. The biggest and the baddest of the filters are the filter presses, also called plate and frame filter presses or chamber presses. These are made up of a series of plates that are indented, and you line the plates with a filter cloth, close the whole thing up, and it creates a chamber that gets fed in with suspension at some initial concentration. The pumps, once it's full of suspension, the pumps keep pushing more material in. It builds up a filter cake on either side of the chamber. At some point, either those cakes meet in the middle, or they stop using the feed pumps. And some of these presses have a squeeze capability, so they can blow the backs of the membrane together and do a filtration process like that, and then open the press up and drop out a solid cake of the solids. This picture in the bottom this is for sewage sludge. You can see this is a couple of meter sized plates. The latest and greatest of these are being built for the minerals industry to process their tailings, and they have a plate diameter of about 5 by 5 meters. So they are absolute behemoths. And the reason for that is the huge throughputs that are required in some of the world's biggest mines. So filter presses, another example. They're quite easy to model, filter presses, because it's all essentially one-dimensional. There's one dimension where everything's just building out the cake. So if you know the compressibility and the permeabilities of the material, you can model this quite straightforward. There are a range of other dewatering technologies and devices out there. I'm not going to go into all of them. Like I said, I could spend a long time just talking about the devices. As a matter of fact, I'm already spent too long on it. They can depends on the particle size of the material, and so I can have, if I've got large particles, I can just put them across a screen and let gravity drain the liquid off. So that's often for the case, hundreds of microns or bigger. You can just use screens. It also depends on the initial concentration. So there are a range of different what are called polishing filters that are used for clarifying liquids. So if I've got a few particles in a liquid, I'll put it through a polishing filter and just to remove those last few particles. There are different versions of belt filters that can have a vacuum. I haven't even started talking about centrifuges. Sand filters are a deep bed filtration mechanism where the liquid trickles into a bed of sand and the particles get left within the sand bed. Screw presses are an Archimedes screw with permeable walls as well as at the end, so lots of different behaviour going on there. And inline flocculation is not really a dewatering process, but it's using the process of flocculation to cause syneresis and collapse of the network to release free water that can then be drained off. Okay, I'll pause for a sec. Are there any questions so far? All good. So as you can see, there's a range of different ways in which I might cause liquid to come out of a suspension. In general, the cost, this is for mineral processing, but as I want to get to lower and lower moisture contents, it generally costs more and more. Okay. This is going to happen because there's a similar effect because of particle size, for example. If I want to go to smaller and smaller particles in mining, because I want to liberate the valuable mineral and make sure that it's at the surface and I can float it off, that's going to have a consequence to my dewatering costs. So recovery of valuable materials, it's going to cost more if I go to lower and lower particle sizes, etc. In general, there are two parameters that are going to be of most interest when we're looking at all of these processes. First of all, how quickly does the water get out, i.e. the permeability, and that's all governed by the solid liquid drag. The other parameter is the concentration that I can get to, or the compressibility. Now, if I've got big, large spherical particles or monodisperse, then it's all going to go to random close packing. Right? Anybody want to tell me what random close packing volume fraction is off the top of your head? Who's listening, or who's gone off to get their lunch?
There must be at least 5 people that know the answer.
It must be at least, maybe I'm not looking at the chat. I get my class to memorize the number because
I just been in a workshop that the guy that actually solved the conjecture of this packing was actually there.
Yeah, right. Okay.
Thomas Hale. Yeah, he proved it.
Fantastic. What answer does he give? Oh, you're muted, Hagen.
No, he did that, not the random close packing, right? That the density is the hexagonal. Yeah.
Oh, okay, right. So usually, about 65% is my normal answer for that. The problem is if I've got smaller and smaller particles with larger and larger interactions, or they're non-spherical or they're polydisperse or whatever it might be, that they're not going to go to that concentration. And in particular, we see a effect of pressure on the concentration that we can get to, the equilibrium extent. So we're interested in this compressibility. How far will we get to? If I waited forever then what would I get to? There's a 0 point at which particles are just starting to touch and will just start to form a network, and therefore just start to have a strength to it. We call that the Joule point, but it's got a very similar name in a range of different fields. The null stress solids is one of them. Civils have a different name. Soil mechanics have a different name for it. Anyway, in chemical engineering, we call it the Joule point. The different devices that I've looked at could either be permeability limited or compressibility limited, which means that we can run it either because we're limited in the concentration that we're getting to because we're not spending enough time in the device. That's the permeability side of things. Or we're simply limited by the physics of it, and that's the compressibility limited. And even if I did wait longer, I still wouldn't get any further because I'm at the physical limit of that pressure that I'm applying. A quick recap of this is the only slide on traditional dewatering theory. If I look at sedimentation of single particles, we can, if it's a low Reynolds number, we can use Stokes' law to describe the sedimentation of a spherical particle. So many of you may recognise that. And if I want to look then at the effect of concentration, as I go higher and higher concentration, there's two effects. One is that the particles are now taking up volume, and so there's a net upward flow of liquid that creates a 1 to the minus of the voidage effect. But there's also an effect of interrupting the streamlines around all the different particles. And so as I get more and more particles, we tend to have a slower and slower settling rate. So we can there's an empirical rule called the Richardson-Zaki equation that says that the settling rate at any concentration will be the settling rate of a single particle multiplied by the voidage, which is getting lower and lower as I go higher and higher in solids concentration, to the power of some value n, which they give as this. That's completely empirical. You can measure this for a range of different concentrations, and you can fit a power law and get these parameters. On the filtration side of things, I typically use a packed bed description of the filter cake that's building up and apply Darcy's law across that filter cake. And because the filter cake is building up as a function of time and directly related to the speed at which you're going through that filter cake, then you end up with what's called the Hagen-Poiseuille filtration equation, which says that the inverse flow rate, T over V, is equal to the viscosity times the specific cake resistance, and I'll come back to this, multiplied by C, which is the cake solids mass per unit volume filtrate. It's a concentration, divided by 2 times the area squared times the pressure drop, multiplied by the volume of filtrate, plus the viscosity times the membrane resistance Rm divided by the area divided by the pressure. So we've got some contribution from the cake, and that's changing with V because we're building up more and more cake as we filter, plus some contribution from the membrane. That's not changing as a function of time because that's just sitting at the bottom. Alpha M is capturing the rate at which it's going through, and that's called the specific cake resistance. Now, the assumption is made that is a constant across, or it's an average value across the whole cake. Unfortunately, measurements show that is a function of pressure. Likewise, C is a value that, well, it's a process-dependent parameter that depends on the initial concentration. But it depends on the initial concentration and the cake concentration. But that is also a function of pressure. And so you can't use this equation if you've got something that varies a lot with pressure, is essentially the message. So it doesn't take into account compressibility, and so it's only useful for large unflocculated particles. As soon as I have some very fine particles where surface roughness or non-spherical shape starts to have an effect, or as soon as I've got some significant interparticle adhesion, then I end up getting compressibility, and so you can't use this approach. So that brings us to the idea of compressional rheology, which was first not quantified, first published by Richard Buskell and Lee White in 1987. Richard Buskell was the head scientist at ICI in the UK, and Lee White was a mathematician at the University of Melbourne. And essentially, it's it's not unique. It's directly related to a range of other theories, and you can relate it back to things like Terzagh's soil consolidation theory and a range of other things. But it's a continuum model of behaviour or phenomenological behaviour. We see these phenomena in our in terms of pressure dependencies, and so we can write down a continuous equation based on the local volume fraction. And so we can do a momentum balance and a volume balance over a volume element of suspension, and balance the different forces that are acting on the liquid and solid phases. And once you do that, you end up with a series of local conservation equations. This is the combined conservation equation for the solid and liquid phases. It's got a term due to the solid liquid drag, which is the difference between the solid velocity and the liquid velocity, scaled with some drag factor. Okay, so R of phi is what's called the hindered settling function, and it changes as a function of concentration to describe the drag. There's a gradient of the solids pressure or the particle pressure, and as long as the pressure is increasing or constant, we can assume that particle pressure is represented by the strength of the material. If I start releasing the pressure, then we've got to worry about elasticity of the bed and various other things, so that doesn't always hold. We also, of course, have conservation of solid and liquid volume, like so. We can then put those tensorial equations into whatever geometry we like. Typically, 1D Cartesian is always nice. And luckily for things like filters and thickeners, it's all typically 1D Cartesian. Centrifuges, you'd need to put it into radial, but the other things we'll need are essentially be able to measure these properties of these materials. And luckily that there's been 20 years of work to go through both the maths to simplify the inverse problem. I have some experimental results and I want to extract the material properties from that, and also the development of the experimental tests. So I've got some slides that go through our regular methodology for characterizing the compressibility and the permeability of suspensions. So for the compressive yield stress or the compressive strength, which this parameter is, as I said, quantifying the extent of dewatering, it's what happens at really long times. Here I've got a picture of what happens if some flocks are settling, and you can see that these flocks form big open space filling networks. If I apply a pressure to that, it makes it collapse. So this looks something like this. The compressive yield stress as a function of volume fraction 0 at the gel point, and typically increases with a power about 5. This gel point can be as low as 1% for sludges and very large aspect ratio needles, attapulgite and various other clays. It can be very low. we typically measure it using a series of different techniques because we need to be able to cover a series of different pressures. So we can measure low concentration values down here from sedimentation, stuff in the middle from centrifugation, and high pressures using filtration. If I have an incompressible material, it's just a straight line on this plot. It's got the gel point is the same as its infinite compressibility, if you like. And so it's just a straight line up and down. Funnily enough, I haven't measured a material yet that is not compressible to some degree, that I can do a sedimentation test on 250, 300 micron big balls of stuff, and I will still get a slightly different value when I do a sedimentation to a filtration test. Pressure filtration tests, we've got there's a range of different devices available to do this. This is what we've got, which is a bespoke filtration device. In particular, we've got a pressure transducer mounted in the face of the piston that allows us to ignore frictional losses of the piston. So we can directly measure the pressure that we're applying to that cake. We can measure the displacement from a linear encoder, so highly accurate measurements there, and it's all controlled with a PC. An example of some results, this is for a stepped pressure compressibility test where we compress it at one pressure until we reach our equilibrium criteria, and then compress it at higher and higher pressures. And from the endpoint at each of these, we assume that that's reached equilibrium, and from that we get our compressibility curve. That's just the conversion there. So that's filtration testing. For sedimentation testing, we can use a very simplistic idea of, so if I sediment a material in the concentration at the top of the sediment is at the gel point. There's no pressure acting on it. But as I go further and further into the bed, the concentration goes up because of the weight of the particles sitting above it. So I can't actually do a test. If I wanted to measure the gel point, I can't do a test where I have zero initial height. It's impossible. So what you need to do is have a series of tests, either increasing concentrations or increasing initial heights, and then extrapolate back to a zero initial height, which is what these results here are showing. This is for a red mud, which is for alumina processing. The particles are red, and the liquid which is at pH of 13, it's caustic, dissolved up with a whole heap of alumina. The particles are red and have settled. And as you can see, as I go to the higher and higher initial heights, the proportion of the sediment to the overall height is decreasing. That's because the sediment is compressing because under its own weight. This is some tests with a water treatment sludge using ferric chloride to coagulate the material. As you can see, the gel point of this stuff is about 1%. This one's about 0.7%. Very low concentrations of solids. Question in there? Sorry, I thought I saw a question come up.
No, I want to remind so everyone, so if you have a question, you can type your question now in the chat box.
Please, you're welcome also to interrupt me. I'm happy to be interrupted at any point if you want me to stop and explain something. So batch sedimentation, we can get a measurement of the gel point. There are much more sophisticated methods of taking the sedimentation behaviour and analysing that, and I'll come to that in a couple of slides, but that also gives you a measurement of the gel point. We can also use centrifugation to look at the compressibility of a material. We put it into a tube. We've got this device in our lab called a lumifuge or a lumisizer. You put your suspension in a tube, it spins at high rates. There's a light source and a detector underneath, and so you can track the transmission through your sample, and you can track the height of the sediment as it's sedimenting. You can do that at a range of different rotational speeds, and from that equilibrium height at each rotational speed, you can back calculate the compressibility. The only issue with this is that the manufacturers only make tubes with a centimetre diameter, and we did a whole lot of work for over about 10 years to show that actually they're too small. You end up, the wall effects are all too significant. So we've kind of gotten rid of this technique, except for the most extreme cases. This works well for nanoparticles, for example, because they never sediment under gravity. The hindered settling function is our parameter that talks about the rate at which the water comes out. And it essentially just accounts for all of the interactions for the drag. Inversely related to a Darcian permeability, if you're looking at Darcian flow through a packed bed, or settling rate. So as RFI increases as a function of concentration, permeability usually decreases as a function of concentration, and settling rate decreases as a function of concentration. The advantage of RFI is I can just define it across all volume fractions, and therefore it accounts for settling behaviour and packed bed permeability behaviour. It's just an empirical value that accounts for that drag. Again, we can measure it using gravity, centrifugation, or filtration. And here's some results for I think this was zirconia off the top of my head. I think it might be a fine zirconia suspension. You'll see here free settling behavior 2 by 10 to the 6, 2 by 10 to the power of 6. And as we increase the concentration, that drag parameter increases by 7 orders of magnitude. So by the time we get to a filter press and we've got it in there at 40 volume percent, our drag has changed very dramatically. Very few engineering parameters change by that many orders of magnitude in the same device. In order to measure the drag across all of those concentrations, we use a range of different techniques, but we can get sedimentation rate behavior around about the gel point, and then filtration behavior at a high concentration.
So Anthony, for the interruption, we have 9 minutes left.
Thank you very much. How many slides have I got? I don't think I've got that many slides left.
Would be good to also have some question time.
Sure.
Yeah.
I'll finish up. We can get, I won't go through the explanation of all of these. We can get rate data from filtration testing. In this case, it's a stepped pressure rate test. So as soon as I've got enough constant slope data here, I step to the next pressure. We can get rate from batch sedimentation. So these are settling tests, and these are the analyzed results. So the analysis works fairly well. Same for the rate of settling in a centrifuge. So we can get PYFI and RFI, these 2 parameters that explain the extent that I can go to and the rate at which it can come out as. If I take my governing equation and I typically can reformulate it, it turns out to look like a second order partial differential equation that looks like a diffusion equation. And the diffusivity is some combination of that compressibility and permeability. And that diffusivity is telling me if I have a change in concentration because of some pressure that I'm applying, for example, how quickly does that concentration propagate through the body? And so it's a really useful parameter to compare different materials. This is a plot out of my PhD thesis, so it's a little bit old now, but it compares things like mineral sludges, which are right up the top here, highly permeable and will get to higher concentrations compared to things like a sewage sludge, which is 7 orders of magnitude worse than the mineral sludges. Other materials don't get to very high concentrations and they sit over here. So water treatment sludges, this is an industrial Myex resin, etc. But we can do it, the same treatment for a whole range of different particulate materials. I've got a slide there on cake washing. I won't go through that, but it looks at basically the efficiency of trying to push a separate fluid through and how quickly do you get rid of the solute that's inside a cake, for example. There's also a bit of work that looks at desaturation. When you look at compressing materials or compressible materials, there's two, and then you're trying to desaturate it. There's two competing pressure terms. One is the compressibility and one is the desaturation or the breakthrough term, which is for the capillary, the strength of the capillaries in there. And so you end up with a really interesting playoff between those two effects. If you understand the compressibility and the permeability, or washing or drying, if you've got those things in your process, you can then create a model of that process. And once you've got a model of that, you can play some games around optimization of design and operation in order to maximize things like throughput as a function of area. So just to summarize, there's a whole range of different types of devices that are used throughout industry. If you're going to look at fine or flocculated suspensions, you need to include compressibility. We can measure those using settling, centrifugation, and filtration. A couple of comments there on desaturation and washing that I didn't go through. And then lastly, models and characterization. So hopefully I've got enough time for a couple of questions.
Thank you, Anthony. Thank you for your excellent presentation. Yeah, we have 5 minutes for questions. So anyone from the audience, so just unmute yourself and ask a question. Thank you.
Hello, everybody. Hello, Itai, Anthony.
Hi.
Very interesting presentation. I'm very sure I learned a lot, but very hard to say exactly what I can learn from, for my research. But I have some question on, about some of, I having some problem that probably I think some of your research or some of the idea can be helpful for my research. For example, I'm interested in, in opposite wave that you're talking about, separation of the solid and fluid. What happens if we have a solid structure? I give an example. We have structure soil that all the particles contact each other and bond their relationship for a long time. But up to one of the loading condition, then the particle becomes separated and becomes suspended, for example. So I think that is quite opposite way that you are doing. So I'm struggling to find out, in soil, we have various particles. We have sand and silt and clay, they all together in the medium. Now, if I want to model that process, I think it's depend on the cohesion and the bonding between particle and negative charge, because some particle have, some particle don't have that sort of the bonding. So what is the potential approach in terms of the particle-based modeling, for example, if I want to simulate that the entire process? You have any idea? I can see the study with a lot of continuum approach. I have an idea, problem, and I'm struggling to find out DM, for example, how to model many particles together in kind of that. Do you have any idea for that?
First of all, is it water that you're using?
Yeah, there's pour water.
Yeah, it's pour water. So no, it's not, but it's not a gas. So you're going to have something to describe the fluid. So if you're looking at a particle scale model, you're going to have to do DEM CFD or DEM, some way of coupling the two.
Yeah.
Because it's going to be the fluid force will be driving that. In terms of the tensile strength of networks, that's not something I've studied. But given that the compressive strength and the shear strength are directly related to each other, I would expect the tensile strength to be directly related as well. Smaller than the shear strength and the compressive strength. You know, the shear strength is orders of magnitude less. Here you're literally trying to pull the thing apart. But I would expect that you could see similar effects in shear flow as you would in a tensile flow.
Yeah. Have some experience with DM-CFD coupling, for example. The major issue we have when we have fluid interaction with the particles, solid particles, that change a lot with the type of particle you have. Yeah. You have granular material that would be easy. We play with drag force, for example. But when we have, cohesive particle, for example, we have the double layer between the particles and the pore water, for example. That linked to the another issue when I had back to 7 or 10 years ago, when we applied the vacuum preloading for the soil. So we want to, reduce the water content, but at a certain level, we can't reduce further. So still a lot of water remain inside the soil, because I think about permeability change, of course, but we also think about the double layer between the cohesive particle and the water. To that level, the vacuum preloading, say up to 80 minus 80 kilopascal, can remove such kind of the water around the particles.
No.
So you're just talking about some of the technique you mentioned is very interesting. So what do you think about the challenge?
Sorry. But you with the 80 kilopascal, it's partially desaturated or it's completely saturated still?
Saturated, yeah, fully. But of course, when we apply minus 80 kilopascal, we see a lot of bubble. I mean, the air comes from the water, pore water inside the soil.
Okay, so it starts and it's not completely saturated when it starts.
Yeah.
Right.
Yeah. When we have different compression, you can see that how the saturation change with that. The saturation decrease. When you reduce the negative pressure, for example, you will see that we have a lot of air come inside the water because it separates the particle together. Yeah. So that's one of our experience when I was in Singapore. We tried to, reduce the water content and increase the consolidation degree of the soil. But we want to speed up that process, but at a certain level, we can't exceed the limit. So I think that's quite similar because we have a lot of sludge and slurry soil from the reclamation from the Singapore port.
Oh, yes. Yeah, I've looked at dredge sediments before.
Yeah. Yeah, a lot of sediment, exactly. Yeah. Anyway, thank you very much.
Thank you. So it's 2 p.m. already. So, but if someone has one very short question, we think we can still take that one. Any one for short question?
I had the short question, but it's probably a long answer, so I don't know if now I can just say it so then we can consider. It would be nice. I feel like Tan was talking about the particle level information. I'm more interested, and I think it was alluded in your talk about the continuum level analogies between your disciplines and in the case of Tan, geotechnical engineering. And I think that you mentioned that several times. So it almost feels like we need a dictionary of terms. So the gel point, it feels to me, and I was just picking up, I said, oh, that looks like the plastic limit. And when I looked at the PY curve that you have, it seems like the sort of the consolidation curve where you exclude elasticity and you think that everything is just plastic. And we normally in soil mechanics also do unloading. So if you change the center. So I'm just curious because I think there's so much to learn by just making such a dictionary of term, and maybe one day we sit together and we just try to understand.
Yep. No, there's a direct overlap. It's of the areas that people work in. We've had a lot of fun playing. I have done odometer measurements and used a triaxial cell. So yeah,
The same. Yeah.
Yeah. Often I find with the soils, it's a lot of measurements are not necessarily taken at a state of knowledge of the system, like, or it's not at a either unsheared starting point or I worry about the shear history of the samples.
Oh, in soil mechanics, there's ways of doing without any shear. We do in triaxial, we do isotropic compression. In fact, in the test that you do, there's always element of shear. So actually, in soil mechanics, we are very careful in eliminating between the shear and the compressive part.
Yes.
So, but not in the 1D compression. There's always element of shear there.
The uniaxial compression always has that.
Yeah.
We had issues though with the triaxial. We couldn't load we couldn't get it to suspensions to have enough physical strength to be able to load it in.
So I wanted to ask, what's the orders of magnitudes of your stresses, like the maximum that we're talking here when you compress in kilopascal or in Pascal, let's say?
In our filter, we go up to a couple of megapascals.
Oh, okay, so it's really high. Well, okay.
Yeah.
Okay. It's very comparable.
Yeah.
Yeah.
Okay.
Thanks. Yeah, it's
Thank you for joining us, and Anthony, thank you for giving the first seminar to us.
It was a pleasure.
It was brilliant. Thank you.
Thank you,
and
Anthony.
Really, really good. So
yeah, we have green days in December, and Anthony has another conference, Australian Career Rheology Conference.
don't log out, people. Follow the link of Wenbin and the two messages. If you haven't done that, do it now and register Anthony. Do come as well, not just your students.
I'll open up the link right now.
Yeah.
Bye.
Not just your students. All right. Thank you so
Thanks
much.
very much.
Bye.
Thank you. Bye.